So let us dive straight to the first one now, which is the power quality. So we want to see what power quality really means. So as you can see on your screen, power quality means the quality of the voltage or the power that is supplied to your system. Okay, that is the quality of the power that is present here on this bus in your MCC. Are we getting it? So now when we say power quality, remember we expect that the power that will be supplied to this bus must be of a definite magnitude. Okay, and then their phase difference, like we said, identified earlier, must also be 120 electrical degrees, since we have deposited those coils on the stator, okay, at that separations to 120 electrical degrees. And then we also expect that input power to be at a particular frequency. Are we getting it? So that is the quality that we are talking about, which means the normal voltage as indicated on the nameplate of your electric motor. So that should be what will supply to the motor system. And then of course, what we are supplying to the electric motor system must be a pure sine wave. Anything that is outside a pure sine wave means that the quality of that power has been distorted. So the how, we will see that as we go along. So now, what are the various power quality issues that can affect the quality of the power that we are actually sending to our electric power system? So they could be actually divided into two broad categories. Okay, we have the steady state variations or event, and those transient or temporary events. So on the steady state event, we see the voltage unbalance. We'll see how it will affect our system later. We'll see the harmonics, what they are, and how they affect the system. Then flickers, voltage flickers, notching, noise. Then on the transient event, we have transients, okay? That is temporary events. Voltage sag, voltage swell, we have interruptions, and DC offset. So we are going to see how all of these actually will affect the reliability of the entire system. Okay, that is the motor system. So let's look at the voltage unbalance. Like we said earlier, the three phase of the power supply must be at the same level, the same magnitude. So if the supply is indicated 415, okay, it means that the phase to phase must be 415. As you can see here, the red phase, the blue phase, and the yellow phase, they must be at the same magnitude. Are we getting it? Then the phase difference also, okay, must be 120 degree apart. Okay, so that is what is supposed to be maintained for our voltage to be balanced. Are you getting it? Then the voltage will not be balanced if any of these phase is higher than the others, as you can see on this other voltage signal, okay, or waveform on the right of your screen. So if you look at it, you'll see that the three phases, they are not balanced, they are not equal. Are we getting it? So once they are not equal like this, it affects the integrity of the entire system, and most especially the electric motor itself. So if you look at the top right of your screen, you will see what you could observe when you use a power quality analyzer on your system. Okay, so as you can see, this is the various voltage levels of the three phases, and as you can see clearly, they are not of the same magnitude. Okay, then the frequency is 50 Hz, which is what is expected if the system is a 50 Hz system. Okay, then look at the phase angle. If this is 0, especially this one is supposed to be 120. If you look at it, we are having 118, which means that it is out of phase by 2 degrees. Then the third, 120 plus 120, we are supposed to have 240. And here we are having 233. Okay, which means that with this reading, we are having power quality issues. Now, what is the level of imbalance in this system? So to calculate the level of imbalance in this system, as you can see, we have the first phase, we have 236.4 volts. Then the second phase, we have 234.5. Then the third, we have 239.3 volts. So we'll take the average of this, okay, which means that we are going to add all of them together and divide by 3. When we do that, we will get an average of 236.7. 236.7 becomes our average voltage. So we'll now look at the difference between each of these phases and the average. Okay, so if we look at the difference, we'll see that on phase 1 we have 0.3 volts, phase 2 we have 2.2 volts, and phase 3 we have 2.6 volts. Okay, so now the highest deviation from the average is at 2.6 volts. So our unbalance will be that highest deviation, 2.6, divided by the average that we calculated earlier, which is 236.7, and that will give us 0.011, which is 1.1%. So the voltage unbalance on this system is 1.1%. So it actually depends on the tolerance of the system. Of course, this will definitely have an effect, as we will see later, 1.1%. Okay, but the allowable range is between 0.5 and 2.5%. Anything above 2.5% is unacceptable, because the effect on the electric motor itself will be very, very catastrophic, and it can lead to the system downtime, okay, or frequent failure, so to say. We'll see how this will also affect the electric motor itself and even the system as we go along. So now look at how the voltage unbalance, okay, this graph shows how the voltage unbalance will affect the temperature rise of the electric motor itself. Okay, so as you can see, a 1% unbalance can cause 2% temperature rise. Are we getting it? So a 2% unbalance can cause 8% temperature rise. 3% unbalance can cause 18% temperature rise. Okay, because that unbalance has a way of an unbalance has a way of affecting the current that flows through the windings at the end of the day. An unbalance of 1% can cause or can result to an unbalance of between 6 to 10% in the amount of current. That is in the an increase in the amount of current that flows through the windings of between 6 and 10%. So that is huge. Okay, so just imagine you have an unbalance of say 4 volts. If you have an unbalance of 4 and one is causing an increase in the amount of current of 10%, that is automatically a 40% increase of the amount of current that is flowing through the windings. And as you well know, the amount of current that flows through the winding affects the amount of heat that is dissipated in each of these windings. From the formula power loss equal to I square R. It is exponential, the effect. Okay, so you see that the heating effect of that small variation or small unbalance is huge as the difference is going up. So voltage unbalance is an undesirable situation in the operation of electric motor. So usually it is recommended that at the input stage from your utility, the voltage unbalance should not be more than between 1 and 2%. Okay, should not be more than 1%. Are we getting it? And because of all of these effects that we are seeing on the screen. So voltage unbalance is an undesirable event. So you check the unbalance at the input, and then that is at the input into the motor system. That is the input into your circuit breaker or into your fuse. Okay, into your fuses at the MCC, and then the input into your motor at the terminal block of the electric motor. So you want to check it to see that they are balanced at all times. Okay, then as you have it here, you also can check whether it is balanced here at this point, whether it is balanced here, okay, and whether it is balanced here, so that you'll be able to zero in on where particularly the unbalance is coming from. If it is not coming from the power supply, it can come from these lines, as we will see later, okay, because of resistance build-up. Are we getting it? So it is very important for us to maintain balanced voltage to our electric motor.